Okay, now we will continue with some properties of the Laplace transform. And as you can see, the structure of this topic, Laplace transform, is quite similar also to the Fourier transform in the sense that we learned the definition first, then a couple of properties of how to operate with them. Fortunately, these two tools, this new new in the course, I mean not new in life, like in normal life. These two tools, these two options, the Fourier transform and the Laplace transform, are linear, as we will mention now. And then since we are using these mathematical options to solve, in the case of Fourier transform, partial differential equations, and in the case of the Laplace transform, ordinary differential equations, the method we will see next lecture, but just to mention a bit now that they are quite similar. We have this new notion, let's say Fourier transform or Laplace transform. We will have a partial differential equation or an ODE, an ordinary differential equation. How do we proceed to solve these equations using these two options? Okay, we pick our equation, could be partial or could be ordinary. We transform the equation, so could be Fourier transform for the partial case, or Laplace transform will be for the ordinary equation case. Once we transform the equation, apparently, so we do that because we will get an easier equation to solve. Then we solve that easier equation, but we don't want the transform of the solution. We want the real solution. So at some point we will also need to anti-transform, to undo the transform. And that's why we saw before, like a couple of lectures ago, maybe last lecture, I don't remember very well, the how to invert, like the definition of the inverse Fourier transform. So today also in the last part, we are going also to see how to undo the Laplace transform. But just to for you to keep this in mind, that the process is quite similar, just that the mathematical offset that we are using is different. So we have a different definition and we have different properties, but the idea is exactly the same. We will need to solve an ODE in the Laplace case, also in this Laplace transform method, and we will have these steps. First, we will transform our ODE, and transforming the ODE is not enough. We need to know some properties, like is this Laplace transform linear? How this Laplace transform acts in when we have derivatives, and also, okay, we can find in our ordinary differential equation a couple of functions, so we also need we need to know how to compute the Laplace transform of those functions. Okay, and once we solve the new equation transformed, we want to go back and recover the real solution, the solution of the equation. And that's why at the end of this lecture we will see how to invert this Laplace transform. Okay, so now let's focus on the properties. So, operational properties of the Laplace transform. As we had for the Fourier transform, we have linearity, which is great, because in the whole course we were working with linear partial differential equations or also linear ordinary differential equations. So if we have to compute the Laplace transform of a linear combination of functions, then that's exactly the linear combination of the Laplace transforms of the functions, okay? Then how this element, this Laplace transform, works with derivatives of function. And you can prove all this stuff by integration by parts, but we are not going to prove it, just mention the properties. If we have the derivative of a function f, then the Laplace transform of this function is equal to s times the Laplace transform of the original function, not the derivative, minus f of at 0. If we have the second derivative of the function, then we have an s squared here, the Laplace transform of f at s, and this, you can see that this is a polynomial, right? This is also polynomial, but just a constant. And here we have a polynomial of degree 1. And for the second derivative, we have next to the Laplace transform an s squared, and then we have next to f at 0 the s, and next to f, the derivative of f at 0, just a 1. Remember that 1 can also be seen as s to the power 0. So in some sense, here we have s to the power 0, s to the power 0, s to the power 1, s to the power 2. Okay, as you can imagine, what's going on for the third derivative. So when we have the third derivative, we have s to the power 3 next to the Laplace transform of f, and this polynomial, which is, okay, s to the power 0 next to the second derivative of f at 0, s to the power 1 next to the first derivative of f at 0, s to the power 2 next to f at 0, and so on and so on. And all these formulas can be proved by the integration by parts. Okay. So for any k, we have this sk next to the Laplace transform of f and this polynomial, which is kind of decreasing the power of s. Okay. So, more properties. The Laplace transform takes powers of t into derivatives. So what do we mean with this sentence? If we have a function times t, the Laplace transform takes this power of t into this derivative of the new variable s. Remember that once we transform our new function, which is this guy, depends on s. Okay, if we have t to the power 2, like t squared, then we have this minus turns into minus 1 square, and the derivative goes to the second order derivative of s. Okay, and as you can imagine, then if we have any power k, we will have a minus to the power k, minus 1 to the power k, and the kth derivative with respect to s of this function. Okay, we are not going to prove this, just keep in mind these properties. Okay, the Laplace transform takes exponential functions into shiftings, which means, okay, we have the Laplace transform of a function times an exponential, and what this exponential does is just shifting here the parameter s. Again, this can be proved just using the definition of the Laplace transform. Okay, now we know we have these 4 properties. Remember, we have linearity, which is great because we are going to work with linear ODEs. We know how the Laplace transform acts when we have the derivative of functions, which is also great because an ordinary differential equation involves the derivative of a function. And then we have these 2 more, a bit more complicated properties, which is, okay, if we have powers of t times a function, we know that the Laplace transform makes these changes, like turns powers of t into derivatives. This is the first, let's say, special or weird or hard property. like not as easy to remember as the other ones. And then we have this other very nice property that exponential functions inside like times the function, and we have, if we compute the Laplace transform of this type of element, then we just shift the Laplace transform of the function f. Okay, with these four properties in mind, let's try to see this example, to understand this example. So we have to find the Laplace transform of this function, t squared times sine of 3t. Okay, so option 1. Remember, at the beginning, in the first part, we only knew the definition, so we can still try. We use the definition of the Laplace transform and say, okay, I want the Laplace transform, I want to compute the Laplace transform of this function. So the definition was that is the integral from 0 to infinity of the function f times the exponential to the power minus st. So now we replace f by its definition, which is t squared sine of 3t. But this is not such a nice integral to solve, right? So we are not going to do this. But instead, we can, option 2, use the properties that we just mentioned, these four properties. Well, okay, linearity we cannot use because this is a multiplication and not a sum, so we are not going to use linearity. But the one that we can use is, okay, this is a power of t, and this is a function, just another function, so this can be called, I don't know, g, so g is here. And we can use the property of that, okay, I know that the Laplace transform takes powers of t into derivatives. So what we are going to have here, okay, let's call this green part, not Greenpeace, because the pronunciation is exactly like the environment company, right? Okay, so this function g equal to sine of 3t, and then we have t squared. So we need to compute this Laplace transform of f. So the only thing that we are doing here in this identity is just replacing the f. Now, this identity, what we did was only like we replace sine of the function for g, just notation. And here we're using this third property, the first, let's say, special or weird property, which is I have powers of t, so the Laplace transform turns this into derivative of s. And we have a minus 1 square and this derivative. Okay, so now, well, this minus 1 square is just a 1, and now we have to solve this. To solve this, we can forget a bit about the derivatives, because to be able to compute the derivatives, we first need to know this, right? The Laplace transform of the function sine 3 of t. Okay, so we need to compute this guy. And just to be more general, we can try to compute the Laplace transform of any sine of alpha t for any alpha in R. Okay, so here we kind of pause the exercise here and try to do this sub-exercise, like this exercise inside the exercise. Okay, so we need to compute this, but we are going to use a trick, which is, okay, it will be easier to think about the Euler's formula because it's an exponential function. So we have the exponential to the power I alpha t is cosine alpha t plus I sine alpha t. So if we compute the Laplace transform of, well, here is just the definition of the Laplace transform. So again, we are going to we need to compute this guy for alpha equal to 3, but just to practice, we are going to compute this for any alpha. And now we will see that it's easier to compute something related to this exponential. So here we are just recalling Euler's formula and the definition of the Laplace transform. Okay, so let's compute the Laplace transform of this exponential coming from the Euler's formula. So here, what we only did in this first line is replacing the exponential by this Euler formula that we have. What we are doing here in the second identity is using the linearity of the Laplace transform. So we can split this in these two pieces and this number goes out. Okay. So that's one piece of the argument, and we stop there and we check other stuff. So on the other hand, by definition of the Laplace transform, which is, okay, you pick your f and you put your f here, we can compute this guy. We have t as a common factor, and this is an antiderivative of this expression. And remember this notation, which means we have to take the limit to infinity and then subtract the value at 0. So what we have written here. Okay, also we could have put this as a common factor, but okay, now it's written like that, so let's leave it as it is. And this limit is, say, 0, equal to 0, so you can compute that. And we got this nice number, 1 over s minus I alpha. And just to write it, this guy a little bit nicer, we multiply by this conjugate, which is just exactly the same complex number, but with plus instead of minus. So, okay, we cannot multiply and not divide by them, because then we lost the identity. So we just multiply and divide for the same number, and just distributing here, we get this expression. So, what's nice about all of this stuff? What did we do so far? We wanted to compute the Laplace transform of sine of alpha t. But instead of that, we said like, oh, look, remember, do you remember Euler's formula with the exponential, which has this cosine and sine involved? So we use the linearity of the Laplace transform to get, let's go back, this expression. But then we use the Laplace transform definition to compute this guy, and we got this expression here. So now if we put the information together, we have from, in one hand, we have this expression, the Laplace transform of the cosine of alpha t, the Laplace transform of sine alpha t, with this plus I. And then using the definition, we get this expression that we can split in these two pieces because of this plus here. And we have this s over s squared plus alpha squared and alpha over s squared plus alpha squared. And guess what? We know that these two guys are identity, right? And we know that two complex numbers are equal if and only if the real part is equal to the real part and the imaginary part is equal to the imaginary part. So we just compute the Laplace transform of cosine of alpha t and sine of alpha t for any alpha in R. So again, equating real and imaginary parts, we get these expressions. So now we know these two new Laplace transforms. And this was a sub-exercise inside our real exercise, which was, in the particular case, with alpha was 3. So let's go back to our example. Now we know that the Laplace transform of sine of 3t at s is 3 over s squared plus c squared, 3 squared, which is this guy here. And now, remember that this was only a piece of the exercise. We need to compute the Laplace transform of this function t squared times sine of 3t. And using properties, we got that the Laplace that we are looking for is the second derivative with respect of f of this Laplace transform. So now we know that is exactly this function, 3 over s squared plus 9, and we have to differentiate these 2 times. Okay, so these 3 can go out of the derivative because it's just a number, and we have to differentiate 2 times this expression that we can rewrite it as s squared plus 9 to the power minus 1. And here we have the first derivative where we use change rule. And then we have to differentiate one more time. So I'm not going to read all the computation, but here we're using the product rule because we have this function times this function. One first step that we did before the product rule is this minus 2 here went out of the differentiation, so that's why now we have a minus 6 here. And then we use the product rule, the derivative of this piece times this one without derivative, and so on, right? So if the computation is correct, what we get at the end, you can check if I made some mistake, and you can tell me. But here is in details all the computation. What we got at the end is that the Laplace transform of t squared times sine of 3t at s is this not super nice function, but we got expression. So what did we do to get this expression? We used the property that the Laplace transform takes powers of t into derivatives of the Laplace transform of this function. Then, as an auxiliary exercise inside this one, we compute the Laplace transform of cosine of alpha t and sine of alpha t. Then we use the information for our particular case, alpha equal to 3. And then we differentiate 2 times this function because we needed that to finish this example. Okay, so let's stop here where we, in this second part of the lecture, we saw properties that will help to solve in the future, so next lecture, ordinary differential equations. So again, these 4 properties: linearity, how the Laplace transform acts with functions, with derivative of functions, this property of this example that the Laplace transform takes powers of t into derivatives of the Laplace transform of the function that is multiplied by these powers of t. And the fourth property, also important, is that if we have an exponential function multiplying another function f, then the Laplace transform of this product makes a shift in the parameter s. Okay, then in the next part we will see how to invert Laplace transform.